All right, welcome everyone. This is SUP401, building resilient multi-site workloads using AWS Global Services. My name is Mike Hagan. I'm a principal technologist at AWS.
My name is James Aitken. I'm a senior software development manager with AWS Support. I'm based out of South Africa, and I own the AWS Health service.
My name is Ryan Schroeder, and I'm a site reliability engineer at Netflix.
All right. So, question for the audience to get started. Has anybody here experienced a dependency failure before? Expect a couple more hands. If you've been using AWS, you probably experienced one or two of those. Anybody here operating multi-AZ or multi-region workloads? Hopefully everybody has a hand up for at least multi-AZ. All right. So a couple different questions. Does anyone in here know which AWS services are considered global? Okay, less hands. And has anybody here heard about a pattern that we call static stability? Okay, even fewer hands. That's great. I didn't know about these things either until I joined AWS, and so this is absolutely the right session and the right room for you to be in. We're going to dive into all of those things and talk about how to use AWS's fault isolation boundaries to build resilient workloads that depend on global services. So for our agenda, we're going to talk about fault isolation and static stability. And we'll go over the different types of AWS services that we have. Then we'll talk about best practices for using global services. We'll talk about the AWS Health service and how you can use that for multi-site resilience. And then Ryan's going to talk to us about a Netflix case study and how they built their system to be resilient using global services as well. So and here, I'm going to hand it over to James, and he's going to talk about AWS's fault isolation boundaries.
Thanks, Mike. So let's begin with the first of the isolation constructs. So the AWS cloud spans 30 geographic regions around the world. Each AWS region consists of multiple independent and physically separate availability zones within a geographic area. All regions currently have 3 or more availability zones. Regions themselves are isolated and independent from each other. This separation between regions contains service failures when they do occur to a single region. Other regions are typically unaffected for their normal operations in this case. Right, so each availability zone in a region is meaningfully distant from all the others, up to 60 miles. That's enough to prevent correlated failures, but close enough to enable synchronous replication between the availability zones. They're designed not to be simultaneously impacted by shared fate scenarios, like utility power or water disruptions, fiber isolation, earthquakes, fires, tornadoes, floods. The separation, common points of failure like generators and cooling equipment are not shared across availability zones, and they are designed to be supplied by independent power substations. Finally, each AZ consists of one or more discrete data centers with independent and redundant power infrastructure, networking, and connectivity in an AWS region. All right, so in addition to regions and ACs, AWS also operates a globally distributed point of presence network, or POP network. The Global Edge Network currently consists of more than 410 POPs, including 400 edge locations and 13 regional mid-tier caches in over 90 cities across 48 countries. These POPs host Amazon CloudFront, a content distribution network, Route 53, a DNS resolution service, and Global Accelerator, an edge networking optimization service. Each POP is isolated from the others, which means an event affecting one POP or metropolitan area does not impact the rest of the global network. Right, so we also have the concept of partitions. AWS partitions are a group of distinct regions where every region is in exactly one partition, and most partitions have multiple regions. The one that almost everyone is familiar with is the AWS commercial partition. That's the one most of the public operates in. There are also partitions for China and GovCloud. Partitions put a circle around AWS accounts, data, and resources, and each partition has its own instance of IAM, or Identity and Access Management. Some AWS services are designed to provide cross-region functionality, such as Amazon S3 cross-region replication, or AWS Transit Gateway inter-region peering. These types of capabilities are only supported between regions within the same partition. You cannot use IAM credentials from one partition to interact with resources in another partition. Clicker. All right, AWS also separates most services into the concepts of control plane and data plane. These terms come from the world of networking, specifically routers. The router's data plane, which is its main functionality, is moving packets around based on rules. But the routing policies have to be created and distributed from somewhere, and that's the control plane. Control planes provide the administrative APIs used to create, read, describe, update, delete, and list resources. For example, launching a new EC2 instance, creating an S3 bucket, or describing an SQ. Those are all control plane actions. When you launch an EC2 instance, the control plane has to perform multiple tasks, like finding a physical server with capacity, allocating network interfaces, preparing an EBS volume, generating IAM credentials, and adding security group rules, and more. Control planes tend to be complicated orchestration and aggregation systems. The data plane, which provides the day-to-day operation of the service, for example, running EC2 instances, reading and writing from the EBS volume, getting and putting objects in S3 bucket, or Route 53 answering DNS queries, and performing health checks. Those are all data plane operations. Data planes are less complicated with fewer moving parts. This makes failures in the data plane statistically less likely to occur than in the control plane. While both the data plane and the control plane are essential to the success and operation of the service, AWS considers them to be distinct components. This separation has both performance and availability benefits. So I'm going to give you a concrete example. We've got EC2, or a simplified version of EC2. And here are some packets moving back and forth between the EC2 instances. Right, so this is the data plane of EC2. So the next day, I show up, and I call run instances to get a new EC2 instance. So I make that API call, and in a few seconds, an EC2 instance starts. All of those operations that I mentioned previously have happened under the hood, like getting an EBS volume and wiring up IAM credentials. That's the control plane. All right, and then now I have 3 EC2 instances with packets moving back and forth. All right, here are some additional examples of the differences between control planes and data planes in different services. So to summarize this section, we've learned that AWS provides multiple fault isolation containers, partitions, availability zones, regions, control planes, data planes, and more. The physical and logical separation of regions and availability zones helps prevent correlated failures. We also learned that control planes are more complex and have more dependencies than the data planes do, and are statistically more likely to fail than the data plane. Right, so now I'm going to hand you back to Mike, who's going to walk you through this pattern that we call static stability.
Thanks, James. All right, so let's talk about static stability, and what this means. So our definition, if you were to go look this up on Wikipedia, if you were to go and try to look at this up in Merriam-Webster, you'd find a whole bunch of different definitions. But the way that AWS uses this term is, what we mean by it is that a system can operate in a static state and continue to operate as normal, even in the face of impaired dependencies or failures in those dependencies. And ultimately, what this means for us is that dependencies are not equal to our destiny. Right? We are unchaining the availability of our systems from dependencies. And so how do we do this? One of the ways we do this is by eliminating circular dependencies. It helps us achieve static stability. If there's an event and two systems that are dependent on each other need to restart, a circular dependency can prevent either of them from recovering. So instead, maybe your system can start and it can become operational, and maybe some functionality isn't available until that other dependency comes back up. And we see this a lot with systems like DNS. Many systems rely on DNS to function. But if DNS relies on any of those systems, it could prevent anything from being able to come back. Pre-provisioning capacity helps us handle the loss of fault containers, like in AZ. It's another approach that we can use to achieve static stability. If you're provisioned ahead of time to handle that kind of failure, you minimize the changes that need to be made, like deploying new capacity, in order to recover from an event. And additionally, using EC2, again as an example, instances take time to launch, right? From the time you take call run instances, that instance actually booting up, running all of your bootstrap actions, takes a lot of time. And if you were deployed, let's say, across 3 availability zones, and you lost an AZ worth of capacity, right, you'd lose 33% of your fleet. And this type of loss could overwhelm the remaining capacity that you have, right? And it could bring your whole service down while you're waiting for new instances to launch. So pre-provisioning capacity is another way that we can be statically stable to failures like an AZ event. Maintaining existing state, right? Using a cache or storing a local copy of data is a way to maintain state. So if we think back to the control plane and data planes, the data plane typically tends to rely on data that arrives from the control plane. But the data plane maintains its existing state so that a control plane impairment doesn't impact the availability of the data plane. Now, the data plane may not see any updates, but everything that was working before the impairment of the control plane continues to work just as it was, right? And that's part of also the reason why pre-provisioning capacity is an effective way to recover from failure, right? Because during that impairment, the control plane and any one of its components has a greater chance of being unavailable than the data plane. And lastly, eliminating synchronous interaction. When you uncouple dependencies and you use asynchronous interaction, you can survive transient failures of those dependencies. Maybe you put some requests in a queue and you process them later. Maybe you have an async job or workflow. But this helps you unchain your availability from dependencies that may be experiencing a transient issue. So let's look at an example for static stability. So here I've got a nice simple design. I have system 1 and system 2. And when the user shows up and they call system 1 queries system 2 returns some data, and we send that back to the user. But being built this way, if system 2 is unavailable, well then system 1 is also unavailable. And if we use the dependency math for availability, we would see that multiplying 2 numbers less than 1 results in smaller numbers, right? So here, we end up with a resulting availability of 99.94%. But let's say we didn't want that. Let's say we wanted system 1 to be more available than system 2. One way we could do this is by using an async or indirect synchronization. Maybe it's a push, maybe it's a pull, but we load the data from system 2 into system 1. So when system 2 is unavailable, when our user shows up and they call system 1, they can still get their data back. What this design means is that system 1 is statically stable to a failure of system 2. Right? And this example is both eliminating synchronous interaction as well as maintaining existing states. So let's take that previous example and make it a little bit more concrete, and we'll relate it back to control planes and data planes. So instead of system 1 and system 2, let's replace those with the EC2 data plane and control plane. And this is how it works in practice. When someone makes a change, say you deploy a new instance, you change a security group rule, create a new subnet, and so on, that's all done at the control plane. The control plane is then also responsible for disseminating that information to the data plane. And what this means is that the data plane doesn't need to make calls to the control plane to discover that information. It already has it. Right? So for example, to avoid disruptions in network connectivity, The Amazon EC2 data plane is designed so that the physical machine on which the EC2 instance runs has local access to all of the information that it needs to route packets to points inside and outside of the VPC, right? An impairment of the EC2 control plane means that during the event, the data plane may not see updates, right? Like a new EC2 instance may not get launched, or a new security group rule may not get propagated, but the traffic that it had been able to send continues to work, right? And so this user is still able to interact with the running EC2 instances because the data plane is maintaining that existing state. So a couple of takeaways for static stability. Right, static stability, its definition means that we can operate in a static state and continue to operate as normal without the need to make changes during the failure or unavailability of a dependency. One of the ways that AWS achieves static stability is by removing control plane dependencies from the data plane in our services. And we also say that taking a dependency on a data plane is better than taking a dependency on a control plane, right? And this is because control planes are statistically, just statistically, more likely to fail, right? And so the more reliable approach is to rely on data planes. For example, relying on Route 53 health checks to fail away from an impaired region relies on the data plane of Route 53, as opposed to needing to update a record directly, right? And we'll talk more about this example a little bit later. And in general, relying on data plane operations for both your recovery path and in normal operations can help make your system more statically stable. And this may include some of the approaches that we talked about earlier, pre-provisioning capacity, or just relying on data plane operations in general. So let's jump into talking about some different types of AWS services that we provide. We have generally 3 types of AWS services that are based on the fault isolation boundaries that James talked about. And AWS services are architected to take advantage of these infrastructure boundaries and the control plane and data plane concepts. So at the highest level, we can categorize AWS services into 3 types: zonal, regional, and global. Zonal services are things like EC2 and RDS. They operate independently within each AZ within our region, but even more importantly, they fail independently in each AZ as well. And so this means that services in one AZ minimize dependencies for services in another AZ. Zonal services allow you to deploy multi-AZ architectures that can withstand the failure of a single AZ. And so for zonal services, they have a zonal data plane and a regional control plane. The second category is regional services. And these are services that AWS has built on top of availability zones. So customers, like you, don't have to figure out how to make the best use of zonal services. We logically group together the service deployed across multiple AZs to present a single regional endpoint. So services like SQS, DynamoDB are example of regional services. And they use this independence and redundancy of availability zones to minimize infrastructure failure as a category of availability and durability risk. And so regions allow you to build multi-region workloads. Regional services, as the name implies, are going to have a regional control plane and a regional data plane. The last category here are global services. Global services are services that don't have resources that are constrained to a single region. And because their resources aren't localized this way, that's why we commonly refer to them as global. But that term can be a little misleading. And so what we really mean by global services is that these services still follow the conventional AWS pattern of separating control plane and data plane. But the service has a centralized control plane in a single region and a globally distributed data plane that exists in every AWS region or within our global edge network. So let's dive into a little bit more about global services. There are really 3 main categories of global services that AWS has. We have partitional services, and those are services that are unique by partition. We have edge services, and those are services that operate in the edge network. And then our third category is not entire services, but specific functionality in a service that has global scope. And so each one of these services in the first two columns has a control plane that's hosted in a single region, and that single control plane can present a single point of failure in your workloads, right? Especially in your recovery paths. The third group of operations also have global dependencies on a single region, and these can also represent single points of failure in your workloads as well. And so I'll talk about these a little bit more. So on the globally scoped operations, resources that require the creation, update, deletion of Route 53 records, right? So for example, every time you provision an Elastic Load Balancer, we give you a DNS name. Regardless of where you provision that load balancer, we have to talk to Route 53 in US East 1 to create that DNS record for you. And this is going to be true for lots of services like RDS, OpenSearch, and many others. For Amazon S3, most of your put and delete control plane actions also have a dependency on US East 1, as well as creating and deleting buckets. Because bucket names have to be globally unique, we have to manage that state and ensure global uniqueness, and we do that centrally through US East 1. Multi-region access points also have a single control plane that's hosted in US West 2. And finally, the last one on here is CloudFront. CloudFront and API Gateway allow you to create an edge-optimized API. When you do that, we create a CloudFront distribution in front of your API. And so when you create that edge-optimized API Gateway, we also rely on CloudFront to be able to do that. So let's look at IAM, and we'll use this as an example to understand a little bit better about how these global services are architected. So here we can see the data plane of IAM, right? It exists independently in every AWS region. And each AWS service in that region interacts directly with the IAM data plane. All of the authentication and authorization of every API call you make using SigV4 is done through that data plane. Then we also have the control plane. And it's what you use to manage IAM resources like identities and policies. So when you call create role, that flows through the control plane. The control plane is also responsible for propagating those changes everywhere they need to go. And in this case, for IAM, the places they need to go is every region within that partition. And so what we see is because these global services have a single control plane, we have to be really careful about the dependencies we take and keep that pattern of static stability in mind. So given that we have different types of AWS services, we can have multi-site workloads that use those fault isolation boundaries. And generally, there are two flavors of multi-site workloads in AWS. We have multi-AZ and multi-region. So multi-site workloads use the zonal and regional services and those fault isolation boundaries to contain blast radius and prevent correlated failure. And they give us the ability to sustain the failure of a fault container at one of those sites. And so when we have a failure that happens, we can evacuate the site. So if we have an impact to a zonal service, we can evacuate an availability zone and mitigate the impact that we see. Similarly, if we have impact in a regional service, say like Amazon S3, we can evacuate that region. If you have a multi-region DR plan, you can fail over to another region to be able to mitigate the impact that you see from that impairment. So we have basic strategies for handling failure of zonal and regional services, right? We can evacuate the site. But I can't evacuate from the globe when a global service is impaired, right? So that's the real question that we need to ask. So what do we do? And how does this distinction of control planes and data planes and static stability, how does this all relate to global services? Well, let's take a look at some of the best practices for using global services safely and reliably without introducing single points of failure. So one of the primary best practices for global services is avoiding their control plane actions in your recovery path, right? Like I've said, because control planes are statistically more likely to fail, and for global services, since they only exist in a single region, relying on the data plane for recovery is a much more reliable pattern, right? And this is a form of static stability. You're making your recovery path statically stable to a failure of a global service control plane. And in fact, you can really apply this guidance to any service, including zonal and regional services. The idea of static stability and removing control plane dependencies can be used anywhere in your workloads. And so here are a few examples of global services and what will work and what may not work in the face of a control plane impairment. Now, these aren't all the global services that I showed earlier, but these are some of the most commonly used ones, and especially when it comes to recovery. So let's take a look at a couple concrete examples of how we can put this type of guidance into practice. So here we have a multi-region setup, and we're using Route 53, and we have a top-level domain name, www.example.com, and right now it points to useast1.example.com, right? When we have a failure and that region fails, what we may be tempted to do is to call change resource record set, update that DNS record, and have it point to another region. What I'm telling you is don't do this. Don't take this approach. Instead, rely on the Route 53 health checks. The Route 53 health checks are part of its data plane. And so when you have a failure in a region, and if you have a health check that's pointing to that region, rely on the health check to discover that failure, or provide your own response to that health check so you can manually fail away from a region, right? And this then relies only on the Route 53 data plane. Global Accelerator, another global service. Global Accelerator provides this idea of traffic dials, where you can dial the amount of traffic you want to send to a region. And again, during a regional failure, if you had this kind of setup, you may be tempted to change the traffic dial via the update endpoint group API and shift your traffic like this. But again, I'm saying don't do this. Instead, rely on the health checks that Global Accelerator provides to detect failure in a region and automatically wait away from it. For IAM, you might have an identity provider, right? Maybe it's one that you're running on premises, maybe it's one you're running in the cloud, maybe you're using a third party like Okta or Ping. Well, when that identity provider has an impairment, you might do something like call create user and create a emergency IAM user. Or maybe your security team has policies that says I can't just have this IAM user with admin rights all the time, so I'll create the policy and I'll create the user, and during that emergency, I'll attach the policy to the user just for the time that I need it. But don't do this. All of that relies on the IAM control plane. Instead, pre-provision that IAM user, take those long-term security credentials, and lock them away in a physical or virtual vault. So when your identity provider is having an issue, you can just access those credentials directly from the vault. You don't need to provision a user, don't need to manage policies. And again, this removes dependencies on the IAM control plane. So our last global service that I'll talk about, CloudFront. So CloudFront is our content distribution network, and it allows you to point to origins to serve your content from. So here I've got two different S3 buckets in two different regions. And so if there's a failure in one region, I may be tempted to call update distribution and change the distribution's configuration to point to another region. Again, don't do this. Instead, use something like automatic origin failover and have that disaster recovery site or that secondary S3 bucket already registered in your CloudFront distribution. So when you have a failure, you automatically switch over to a different origin. Or if you need something that's a little bit more flexible, you can use CloudFront functions and dynamically change where you route based on events that you control. And so you can use CloudFront functions as well as part of the data plane of CloudFront to be able to route traffic away from an impaired region. Okay, and so the reason that we spent the first part of this session talking about control planes, data planes, and static stability is that they're really critical for understanding how to take dependencies on global services without introducing single points of failure. Right, so our takeaways for global services, we have 3 different types of global services: partitional, edge, and globally scoped operations. Global services have a single control plane and a distributed, highly available data plane. We want to avoid control plane dependencies in global services, especially in your recovery path. And one way to do that is by implementing static stability. Make yourself statically stable to the failure of a control plane. And then understand what will and what might not work during a control plane impairment of a global service. And then finally, pre-provision resources that have single region control plane dependencies. So anything that relies on Route 53 or S3 or CloudFront, pre-provision those resources, and that'll help make your workload more reliable and resilient to failures of a global service. Okay, so I'm gonna hand it back over to James to talk a little bit about AWS Health.
Thanks, Mike. So implementing observability best practices is imperative for building resilient architectures. You can use the AWS Health dashboard to understand when AWS events might be affecting your workloads and when it may be necessary to execute your recovery actions like site evacuation that we described earlier. All right, so we frequently hear from our customers that when one of their applications goes into alarm, it can be challenging to understand whether the issue is coming from their own code or is actually an issue with the underlying AWS resources. One of the main purposes of AWS Health is to help you quickly root cause the issue as a challenge with the underlying infrastructure. So AWS service teams make use of AWS Health to tell their customers about planned or unplanned events that may be impactful to them. When a service, like in this case Lambda, experiences an operational issue, an event is created in the AWS Health service, either automatically or through our internal incident management process. We make these events available through our console experience, the AWS Health dashboard, which consists of a service health view, which is formerly known as the service health dashboard, as well as an account view, as well as an organizational view for those customers that have implemented AWS organizations on their accounts. We also offer programmatic access via the AWS Health APIs. These are available to customers with business or enterprise support plans. The AWS Health APIs also provide account and organization views. The organization view provides a convenient aggregated view of all your health events across all accounts in your organization delivered to the management account. For those that prefer event-based integration, we deliver health events to Amazon EventBridge. And in the cases of programmatic integration, you can have these health events delivered into third-party CloudOps tooling or your in-house tooling, where CloudOps dev teams may be alerted to the issues, or else automations may be run in order to prepare for your failover strategies. So the AWS Health issue category is used to notify customers of these unplanned events that may be impacting them. Included in the operational issue category are service events, as well as account or resource-specific events. Since AWS Health is critical to letting customers know when AWS events are impacting them, it's imperative that AWS Health itself is resilient to failures. AWS Health is a global service deployed in a multi-regional active-passive configuration using these best practices that we've just been talking about. We use DynamoDB, global tables replication, to ensure that health events are continuously replicated between the regions. We use Route 53 failover routing to determine which endpoint is the active endpoint. So when you want to access the health service, what you do is a lookup against the global.health.amazonaws.com domain name. In the normal case of operations, when health checks are succeeding for both endpoints, Route 53 will return the active endpoint or the primary endpoint, And then you'll use this endpoint to call the active endpoint. Now, when there's an operational issue in the primary region, which happens to be impacting the AWS Health service itself, Route 53 health checks will begin to fail. And now, when you do a query against the global health endpoint, the secondary endpoint will be returned, and you'll use this address to call the active endpoint. When the operational issue recovers in the primary region, events that were created in the standby stack will be replicated back to the primary region. And also, health checks will be succeeding against both regions, and DNS resolution will resolve back to the primary region. So the key takeaways for this section on AWS Health is that as part of your shared responsibility model for resiliency, you should be implementing observability best practices by integrating with AWS Health. AWS Health will be providing you with notifications about planned or unplanned events that may be impactful to your workloads. And the AWS Health operational issue category informs you of any ongoing AWS infrastructure events. Enable AWS organizations for AWS Health as a convenient way to aggregate a view of all operational issues across all your accounts within the organization using the AWS Health dashboard or the AWS Health APIs. And finally, AWS Health provides a highly available API endpoint that uses the Route 53 data plane to manage failover between regions. I'm now going to hand you over to Ryan for the Netflix case study.
Hi, so my name's Ryan, and I'm a member of the core team at Netflix. Our team is responsible for the availability, reliability, and resilience of the Netflix service, and we are the first responders for any availability impact. Today, Netflix runs a multi-region active-active architecture, but this wasn't always the case. To understand how we got here, we need to do a brief history lesson. The resilience story at Netflix began in 2011 with the advent of Chaos Monkey. The goal of Chaos Monkey is to force developers to design around failure by randomly terminating EC2 instances in production. This practice of intentionally degrading the infrastructure in a controlled way gave rise to the discipline of chaos engineering. As Netflix grew into 2012, so did our global footprint. We launched in several countries that year and spun up our first infrastructure in EU West 1. Chaos Monkey grew into Chaos Gorilla, which would simulate an outage of an entire availability zone. However, at that time, each region still operated independently from each other. That decision was put to the test on Christmas Eve 2012. Netflix experienced a significant regional outage for 6 hours. The specifics of the outage are well documented, but we learned our lesson. We need to take control of our own availability by moving to an active-active, multi-region deployment across the AWS regions in which we operated. By the end of 2013, we had a working solution, but it took over 2 hours to do a single failover. The act of evacuating out of an entire region and the tooling to support that is known as Chaos Kong. By 2016, automation had reduced the time it took to do a regional failover to 45 minutes, but we knew we could still do better. We launched Project Nimble, further reducing the failover preparation time down to just 5 minutes. Since that time, the Netflix architecture has evolved and adapted, but one of the guiding principles has always been to design for and account for the need to maintain regional separation and the ability to completely shift traffic out of one region without impacting our members. Which brings us to today, where we regularly exercise our ability to do a failover, and we are even able to start the process with a single chatbot command. So how does this work in practice? Well, to start, we first need to talk about how our team typically gets engaged. For the core team at Netflix, we are primarily concerned with a top-level metric called starts per second. Every time a Netflix member starts watching a piece of content, we count that event as one start event. Across the globe, millions of people are choosing to watch Netflix every minute. We track these events at a regional level, and if you sum these events up across all regions, you get a global view of starts per second. If these metrics deviate significantly from the baseline that we expect, our team is paged to start investigating. If the impact is determined to be isolated to one region, we start the failover process. Because we run in an active-active configuration, each region runs an identical copy of the infrastructure. Over the years, we've ensured that within each region, each service has what it needs to operate without relying on anything from any other regions. Within a region, we operate across multiple availability zones. There is a link between regions that maintains data replication of member data. This includes all their data, from viewing history, to watch list, to member preferences, even bookmarks. Having the data globally replicated allows us to seamlessly move traffic from one region to another without them noticing. When we detect an impact and decide to fail over, member traffic is completely shifted out of the impacted region and absorbed by the remaining regions, resulting in this. Since every region is running the same set of infrastructure and the data is replicated, the process is as easy as scaling up, shifting traffic, and then watching for recovery. Once we do see recovery, we can direct our focus to figuring out what went wrong and correcting it. Once the issue has been resolved, we restore traffic back to a balanced distribution. Since we rely on auto-scaling to right-size the number of instances that each service needs based on the incoming traffic, as part of preparing for evacuation, we must scale up our savior regions. Some of the services that we run have long startup times, upwards of 20 minutes. During an impact to availability, that's too long to wait. So to reduce the scaling time, we started a project called Nimble. Using the predicted traffic shift at any time of the day, Nimble will pre-provision the required instances needed to support failover, but it does it in a separate, non-active ASG. During an evacuation, since the instances are already up and running, all we do is transplant the instances by detaching them from their Nimble ASG and reattaching them to their active ASG. This, along with continual improvement to the automation, has reduced the time it takes to prepare failover from 45 minutes down to 5. Once the system is scaled up, we're ready to shift traffic. This too has evolved over the years, but still fundamentally relies on updating DNS records. For most of our traffic, this DNS routing is done by our Open Connect infrastructure. It has a predefined policy in place for each failover scenario, which is deployed ahead of time and updated regularly. During failover, we make a change to the control plane to set which policy is used. From there, the data plane is responsible for communicating that update to the Open Connect appliances that are routing traffic. We also update our Route 53 DNS records. Since DNS updates are not always immediate, or in the very rare case of a Route 53 control plane outage, we also take the added measure of proxying any remaining traffic from the evacuation region to the savior regions within Zool, our cloud gateway. This time-lapse video is an actual failover using our real-time monitoring tools. Traffic shifts from the region on the right into the other two regions, all while the top value that measures starts per second remains smooth and constant. So what are the key takeaways from this? Well, first and foremost, by adopting an active-active model, we ensure that all of the infrastructure we need is always provisioned. This makes sense because it's serving traffic under normal operations. Failover, then, is reduced to just scaling up the unimpacted regions and moving traffic. Our system is architected to leverage the fault isolation boundaries provided by AWS. Second, we integrate with the AWS Health API to get early indication if there are problems in a region. If we think it may impact our service, we proactively evacuate the region until the issue has cleared. Third, Good measurement of what success means helps us know when to perform a failover. Identifying key metrics that define service health make determining impact analysis that much easier. For us, by reducing that to a single metric, we can make critical, timely decisions and get on the road to recovery. Fourth, it's important to exercise these failover paths regularly. We do this multiple times a month, both for practice and when the need arises. In fact, we perform failover more often to recover from outages of our own making rather than a result of any particular AWS service impact. After each failover, planned or unplanned, we scrutinize the metrics, looking for any systems that didn't behave as expected and prioritize fixing them. And finally, adapt internal operations to support your impact mitigation strategy. Engineering teams at Netflix are aware of the importance of regional failover and adjust their operating practices accordingly. Config changes, deployments, and features should all be rolled out according to your failure domain, which for us is region by region. If we identify something that is not regionally isolated or jeopardizes our ability to perform a failover, we work with teams to prioritize those changes above all else. And that's how Netflix runs a resilient multi-site workload using AWS services.
Thanks, Ryan. Really, really awesome to see what Netflix has built over the past 10 years. They're an incredible customer. So just to finish up, I've got a slide here with some additional resources. A majority of this presentation is based on the white paper at the very top here, AWS Fault Isolation Boundaries. And then there's some additional blog posts and white papers that you can read about other patterns on how to do site evacuation and how to build DR mechanisms using different services like Amazon Route 53. So again, we talked today about fault isolation boundaries, control planes, data planes, static stability, and best practices for using global AWS services and how to safely take dependencies on those to build resilient workloads. I want to thank everybody here for attending today. Hopefully this was very informative for you, and you can use some of this information to help make your own workloads more resilient. Thanks so much, everyone.